Hello, a very good morning to each and every one of you here. My name is Shihab Khanur. So we are a group of researchers from University of Malaysia, Perlis. So today I'll be presenting one of our research paper with collaboration with SIG University. The title is Orbital Angular Momentum Vortex Waves Generation using Textile Antenna Array for 5G wearable applications. So let's begin. So basically, this is the agenda for today. I'll be covering a lot of things in a very short amount of time. Okay, so let's begin. In our wireless communication sector or field, every generation or every G refers to 10 years. So the fundamental objective of new generation of wireless communication system is to improve the user's experience, to come up with a new infrastructure so that new applications can be deployed for our daily lives and to overcome the drawbacks of the previous generation of wireless communication system. So for instance, the fundamental objective of the deployment of 4G was to increase the data rate. So the data rate was increased from 2 Mbps back in 3G to up to 100 Mbps in 4G. So the major focus was on the data rate. But when it comes to 5G, it is a whole different scenario because 5G not only focuses on one thing, rather it focuses on three major things. So the first one is EMBB, which is enhanced mobile broadbands to increase the data rate and to increase the channel capacity. The second one is MMTC, which is massive machine type communication. So the major focus of MMTC is to connect massive number of devices under one network. And the third one is URLLC, which is ultra reliable low latency communication. It focuses on the latency to be less than a millisecond. So this is extremely important for delay sensitive applications such as autonomous vehicles where the reaction time is very important. So undoubtedly, the demand for wireless devices are increasing exponentially because we are using wireless devices for our everyday life. Uh, at the same time, the demand is going to be increased in the coming future as well. Our infrastructure is same. So the service providers must come up with a new solution to make sure they allow massive number of users to use their services with a degrade in performance. So we can see on an average, in 2022, a person has 3 to 4 wireless connected devices. And from this graph, we can see on an average in 2022, a person consumes around 9.1 GB of mobile data every month. And it is going to be increased in coming future as well. So to overcome this challenging, to make sure everyone can use the frequency spectrum properly without any degrade in performance. So the wireless transmission capacity has to be increased. So fundamentally, there are three major ways through which we can increase the wireless transmission capacity. So let's start with the first one, which is the modulation order. So in short, we need higher modulation order to increase the wireless transmission capacity so that because if we have higher modulation order, we can send more bits per symbol. However, for a specific channel with a specific bandwidth, we have already reached the maximum limit of data rate. If we can recall back the Shannon's theorem, the great American mathematician Shannon's theorem, which links the data rate, bandwidth, and a signal to noise ratio of a channel. So for a channel with a specific bandwidth and signal to noise ratio, there is a maximum limit of data rate. So beyond that, we can go there. We cannot go. So modulation order, it is not really an effective solution to increase the wireless transmission capacity, considering such huge demand. So the next one is the transmission bandwidth. So our frequency spectrum is already a very congested one. So we have different channels allocated for different applications. So if we increase the bandwidth of one channel, it might interfere with the channel of another application. However, what we can do is maybe we can use the unused high frequency spectrum. However, considering our current infrastructure and considering the current devices that we have or the hardwares we have, it is not competent enough as of now to work in such high frequency. Hence, transmission bandwidth, it's not going to be an effective solution for the current scenario. Now, what we are left with is spatial multiplexing order. So basically, in spatial multiplexing order, what happens is the main data, it breaks into smaller data packets, and then these data packets are being transmitted separately or individually. So when it comes to transmission of data individually, that's when the role of OAM waves comes in. So OAM waves is nothing but an electromagnetic wave, but there is a presence of phase factor exponential of topological charge L and phi, which is azimuthal angle. This phase factor is not present in linearly polarized or circular polarized waves. Because of the presence of this phase factor, so the phase distribution of the wave, it tends to be spiral in shape. So this is how the phase distribution looks like. So this is the spiral shape. And having such spiral phase distribution, it leads the waves to be propagating in helical shape. So this is how the helical shape looks like. So, and in OM waves, we have something called topological charge or mode. So topological charge basically determines the number of twists or rotation in one complete cycle. So topological charge or OM mode 1 means there will be one twisting in one complete cycle. If we have two, if we have mode 2, then there will be two twisting in one complete cycle. So this way we can have, theoretically, we can have infinite number of OM modes. And surprisingly, these OM modes are orthogonal to each other. So being orthogonal, so they don't interfere with each other. This way we can increase the spectrum efficiency. So what OM offers us? So let's start with the spectrum efficiency. As mentioned earlier, we can have infinite number of orthogonal OM modes. So these modes can be assigned to different users and so that they can use the same channel at the same time without any requirement of additional resources such as frequency, time, or power. So this way, numerous users can use the same channel. They will be assigned modes which will act as a sub channel, and they can use simultaneously the same channel. As a result, the overall spectrum efficiency can be increased. Higher channel capacity. So basically, channel capacity means the number of users. So as mentioned earlier, we can have infinite number of OAM modes, and these modes are orthogonal. So we can assign a lot of users in our channel using these orthogonal OAM modes. And these OAM waves, it's provide a new multiple access system that is called MDMA, which is mode domain multiple access. So here, different modes are assigned to different users. Unless like the previous one or the conventional one, such as the FDMA, where you allocate different frequency, or TDMA, where you allocate different time, or CDMA, where you allocate different code for different users. But in OAM, it provides MDMA, a new type of multiple access. So these are basically the great minds who came up with this concept. So this is just to show gratitude and respect to this great mind. So let's start with Dr. Les Allen. So in 1992, he is the first one to find out that, okay, we can have a phase factor in EM wave. So but his research was focusing on optical communication. So 15 years later, in 2007, Dr. Bothide, he, for the very first time, he experimented OM waves in our radio domain. And in 2012, for the very first time, Dr. Fabrizio Tamburini, he has conducted OM radio waves based experiment for real world settings. So we can see it is, I mean, the very first experiment, proper experiment, was in 2012. So still it is kind of a new topic. Okay, let's move on to the wearable device. So in 21st century, the demand for wearable devices are massive. So we use wearable devices for firefighting, for military purposes, for health monitoring, and so on. So if we look at this graph, it can be seen the revenue of wearable devices has increased exponentially compared to 2013. In 2020, the revenue was above 20 billion, 20 billion US dollar. And in 2013, it was less than 5 billion. So this shows that the demand is increasing for the coming future as well. So when we talk about, advantages of wearable devices. So wearable devices are inexpensive, lightweight, thin, comfortable, low maintenance, and robust. So when we talk about wearable devices, so for any wireless devices, the presence of antenna is very important. And for wearable devices, having hard antenna or rigid antenna is not really preferable because the wearers will not be comfortable. So having flexible antenna is a great plus point to deploy wearable devices. So we can use textile fabric as the antenna, which can be deployed for wearable devices. Okay, so in one hand, I have the new concept of OAM waves, and on the other hand side, I have the concept of textile antenna. So that's what I merged together to come up with this research, which is OAM waves for wearable applications. So talking about our antenna design, so I have used the concept of microstrip patch antenna, and my research was focusing on the N77 band, which is 3.3 gigahertz to 4.2 gigahertz. So N77 is one of the new radio bands of 5G, and I have used the microstrip patch concept, and the substrate that I have used is felt with permittivity 1.44, thickness 3 mm, and loss tangent 0.044. So felt is a very robust fabric, and it is available in the market. And for the ground plane and for the radiating patch, I have used super shielded electrotextile. So the best part of using super shielded is it doesn't peel off easily, and it can be easily mounted on the substrate just with maybe by using an iron. So we have the four patches here, as you can see here, and the antenna dimension is 156.5 mm by 170 mm. So basically, the design is uniform circular array antenna. As you can see here, the patches are being arranged in the form of circular array, and the radius from the center to the center of the patch is uniform, is same for all the patches. So in uniform circular array, what happens is using uniform circular array to generate OAM waves, so every patch should have a phase difference. So we have this formula, which is phase difference equals 2 pi into OAM mode divided by n, which is number of radiating patches. So our focus is uh, mode 1. So 2 pi 1 divided by 4. So it will be like 90-degree. So every patch should have 90-degree of phase difference, and we can achieve the phase difference by altering the feed line length. So we designed based on this formula, and when we simulated it, we have observed that the patch one, the phase it is 0.72 degree, patch 2 88, patch 3 177, and patch 4 268. So it can be seen it is close to 90-degree. Okay, so let's start with the result and discussion. So the very first parameter that we checked is the S11. So our focus frequency or frequency range was 3.3 to 4.2, and we can see that yes, our proposed textile antenna operated within this frequency range with S11 below -10 decibel, and the bandwidth covered was around 81.7 megahertz. And talking about the phase distribution and intensity distribution. So let's start with this one. So we can see the phase distribution, it is spiral in shape. So because of the phase factor, the antenna, it radiates OAM waves, which is spiral in shape, and the wave is propagating in helical in shape. As a result, we can see this phase distribution, which is spiral in shape. Now we have the intensity distribution. So one of the way we can confirm the generation of OM waves is this black dot, black donut type structure. We call it vortex core, or its another name is phase singularity point. So since the wave is propagating in helical shapes, so as a result, in the center there is no radiation. That is the reason it is empty. That is the reason the vortex core is darker in shape. And talking about the radiation pattern, well, the 2D polar form, we can see there is a null in the board side direction. So the board side direction is basically the main propagation direction. So because of the arrangement of the patches, the 2D polar form, there will be a butterfly type shape or a null in the board side direction to confirm that yes, OM wave has been generated. And talking about the gain, so at 3.86 gigahertz, our proposed textile antenna obtained a gain of 2.83 decibel dBi. So when we talk about body-centric devices, so the calculation or the measurement of specific absorption rate is very important because our human body is heterogeneous. Okay, it is high dielectric constant and it tends to be conductive because of the presence of water molecule. So before any deployment of wearable devices, it needs to make sure that okay, it meets the threshold value determined by the FCC or the International Commission of Non-Ionizing Radiation Protection. So this is the permittivity. So we have the three layers. So we have the skin, fat, and muscle. So these are the permittivity, conductivity of human body, the density. So based on that, I have designed a human phantom on CST simulation software. As you can see, here three different layers of human body. And then on top of that, I have put our proposed antenna. And it can be seen that for 1 gram of tissue, okay, the value that we got was 0.0128 watt per kg. And it's within the accepted range because the maximum limit can be 1.6 and our value is 0.0128. And for 10 gram of tissue, we have obtained 0.0089 watt per kilogram, whereas the maximum limit is 2 watt per kilogram. Therefore, our proposed antenna, it can be deployed for body-centric communication system. And talking about the OAM mode purity, so OAM mode purity is very important to make sure that there's a reliable data transmission has taken place using OAM waves. So OAM mode purity, what it means is, so the OAM waves, it can have a lot of different modes. So since OAM waves have energy, so the energy should be focusing more on our desired mode. So in our research, we focused on mode 1. That is why we can see among other modes, the most of the energy is allocated for mode 1. So it shows, yes, we have successfully generated mode 1. So if we have higher mode purity for our desired mode, it means, okay, there will be less crosstalk. So for example, if we wanted to generate OM mode 2, then the mode purity at OM mode 2 has to be higher. So since our research focuses on mode 1, so we have successfully generated OM mode 1. So in conclusion, so this is for the very first time in the world, to our best knowledge, like OM waves is being generated or attempted to generate OM waves using textile fabrics. So previous methods included the hard substrates such as the FR4, then Rogers, and so on. For the very first time, we in the world, OM waves using textile fabrics has been generated. So there are four parameters that we need to consider to confirm that we have generated OM waves. So the first one is the phase distribution. Yes, we have confirmed that because we have seen that we have obtained spiral phase distribution. The dark circle in the intensity distribution, yes, we also have obtained that. And then null in the board side direction, yes, in 2D polar form, we have found out that there is a null in the board side direction, and the mode purity is higher for the desired mode. Yes, for mode 1, the purity was highest for our desired mode. So the next phase of this research can be the actual fabrication of OM-based textile antenna. So this is our research will provide a framework and a reference for the researchers and the engineers in the industry to design a wearable-based textile antenna for the generation of OM waves. So these are the references that have helped us to carry out this research. So having said that, thank you very much, and your questions are most welcome. Thank you. Thank you once again.